Sounds good. 10 to 15 minutes. All right. Very good. Okay. So I, this screen is not touch screen, right? It's not touch, is it? No, not touches. That's all right. If I need to write, I will go there. But I think I can use some little markings here. That should be all right. But I cannot write. If I need to write, I will go there. No problem. Yes, all right. Good morning, everyone. Morning. All right, so yesterday we had two classes, and then we went through some introduction about power electronic converters. And then one thing we realized is that a converter, if you just want to apply a duty cycle and operate it, it will not be very robust. That's the terminology that we use. Or you can say it will be very sensitive to any uncertainty or change that you may have in the system. If the voltage, you assumed it to be 100 volts, but it turns out to be 98 volts, then it's not going to give the result that you want, and it could be significantly different. If the voltage changes 2% and your result also changes 2%, that's acceptable. But if the voltage changes 2% and your result changes 40%, nobody accepts that from you. So for that reason, let's do a sensitivity analysis, because this topic is sensitivity now. Our circuit is sensitive to some parameters. Let's say the input voltage, the output voltage, the resistor. Find out an equation for the sensitivity, and then looking at that equation, we can find out how we can fix the problem. So sensitivity analysis, this is a relatively standard sensitivity analysis that I explain here. Sensitivity function, you might have seen it in some control courses. Sensitivity of a variable y here with respect to a parameter p. By definition is, okay, you change the parameter, delta p, and then look how much y changes, delta y. So the ratio of delta y over delta p, and then you can normalize it to make it like percentage type. So delta y over y divided by delta p over p. So that will be p over y, delta y over delta p. That represents how much the output y is sensitive to the parameter p. So mathematically, we can approximate this one and use this partial derivative, the partial derivative of y with respect to p. So now if you have for any circuit, any system, an equation for y, if you can manage to derive an equation, normally we can do that, then you calculate this expression and then you see the sensitivity function. For instance, for the buck converter, we were talking about the power. Let's say output is power at the B side, which is equal to the A side, doesn't matter, which is equal to current into the voltage, right? And the current is VAM minus VB divided by R multiplied into VB, so you get this expression for the output Y. So output is a function of VA, VB, R, all these three parameters of the system, so you see there already, and the modulation index. So if you know all of them perfectly, then you can calculate y. But the problem is these things will change. So for instance, let's look at other sensitivities also. Sensitivity of the output with respect to R, calculate similarly. And really, I expect you when you get home and when you receive the files, you can start playing and derive these equations. I cannot derive them in details, but please do it for your education. And then you realize the sensitivity is -1. So what does this mean, sensitivity is -1? Means that if R changes 1%, let's say up, if R goes up 1%, Y goes down 1%, right? The same thing for this one. And then sensitivity of the output with respect to VB, you can derive a similar expression. Now, these expressions, you can evaluate them at the rated values. So our rated values is 100 for the voltage VA. modulation index is 425, and VB is 40. Now, if you evaluate them, this one will be 15%, right? And with respect to VA, if you evaluate it, it will be 17%. So that means if your voltage changes 1%, the power, depending on VA or VB, if your VB changes 1%, your power will change 15%. Or here, if your VA changes 1%, your power will change 17%. Yesterday, if you remember, we changed them 2%. 2%, the power will change 34%. So that was the numbers. You can go back and check. These are basically. So this is a very standard sensitivity analysis, but at the same time very useful. If you manage to learn how to work with the sensitivity analysis, a lot of problems in your research you can manage to address similarly. Okay, now we managed to calculate and understand what is happening, but how we can fix it, how we can fix the problem. If you really look at the sensitivities, the reason that these sensitivities are large is because this R is small, right? So if you really look at these sensitivities, all of them, they depend. This R here is the denominator, right? And this also, if you express it in terms of R, because VAM minus VB is the voltage across the resistor, so it's very small. So again, denominator here is very small because R is very small. And remember, in power electronics, we don't want to insert any resistance in the circuit, so we cannot increase R. Because even if you add a tiny amount of resistor in a 10 kilowatt inverter or converter, you will realize that the power loss significantly will go up. And then you cannot handle to dissipate that power loss. So in order to fix that problem, the method that we use is what is called virtual resistance. So can I virtually add a resistance to the circuit to increase this R in terms of sensitivity, but without adding to the power loss of the circuit? And the answer is yes, we can do that. The way to do is this one. Look at this model of the converter that we derived yesterday. And it's a different color, it's a gray color, and then this is kind of light blue color. So let's measure the current. You put a current sensor, you measure the current, multiply into K, bring it here, and then put it at a subtraction block here, and then generate modulation index from the output of the subtraction block. And then you can call this modified modulation. Now I'm going to prove very quickly, and it's not really difficult to prove, that now for this system, the sensitivity, the numbers for the sensitivity significantly will go down by choosing this K properly. So sensitivity of the output with respect to R for this circuit will be negative R divided by R plus RV. What is RV? RV is equal to K into VA. And sensitivity of Y with respect to VB now becomes the same expression we had before, but now instead of M, we have M prime here. And M prime is not a modulation index, so it's a modified modulation index. So the number for M prime is different now. So this quantity in the denominator can become large. And the same thing here, right? And I have shown that here. So basically, you choose K as a parameter, K into VA, that will be a virtual resistance that is added to this circuit. Because if you look at the transfer function of this circuit, this new circuit, transfer function is this. So compare this one with this transfer function we had here. Did I write in? I should have written again, so that the standard transfer function that we had, this one. VA divided by ls plus r. So the standard transfer function is VA divided by ls plus r. Now the transfer function of this modified system with this added branch is equal to this one. So you see that this R is added to RV. And that is why it is called virtual resistance. In other words, this feedback that you add to the circuit behaves like adding a resistor to the circuit. But that resistor, you don't add it physically. You only add it in the software. So it doesn't generate or doesn't cause any power loss. It can only change the transfer function without causing a power loss. And it changes the transfer function properly such that now we don't have that problem of small r. So we have large r. And sensitivity functions, all of them will decrease with the same proportion. For instance, if you choose RV equal to 9R, let's say you choose RV 9R. Now you have R over R plus 9R becomes R over 10R, so it becomes negative 1 over 10. So you decreased sensitivity 10 times. And similarly here. So all the equations here are kind of inversely proportional to RV. So when you increase RV, proportionally sensitivity will go down for all parameters. Okay. Later on, when we get into the control, maybe tomorrow, yes, today, because I talk about control in the second and third classes, but tomorrow we will start using the control. I will explain to you why we should not choose this K too large. Because this is tempting. Some people like to say, okay, if I can decrease the sensitivity, why not decrease it as much as I want? Like make it 1,000 times or 10,000 times. But that will cause other problems. Always in engineering, keep in mind as researchers and graduate students, if you see something, you can increase one parameter and things get better. Don't get tempted to increase too much, especially in control. Because in the simulation, you may see, oh, things become much better and really significantly improved, but then they will cause problems in practice. They cause practical problems. So I will cause about practical problems of this aspect or this virtual resistor if you choose K too large. Okay, tomorrow. All right. So now let's go back to our example. See if this feedback can solve the problem we have. So this example, go back later and look. All the items are the same items we had in the previous class, but now I'm going to consider a virtual resistance of 20 R. And R, if you remember yesterday, was 10 milliohm. So 20 into 10 milliohm becomes 200 milliohm. So that will be our virtual resistance. If you want to calculate K, K will be RV divided by VA, so 0.2 divided by 100. So your K, feedback gain, is 0.002. Then modified modulation index at the rated operation is M plus Ki bar from this diagram, right? This modulation index is M prime minus Ki bar, so M prime is M plus K into I bar. So you calculate that for 425, and that gives you 925. And remember, this M prime is not modulation index anymore, so it doesn't have to be a number below 1. If it's even above 1, that's all right, no problem. But M should always be between 0 and 1. Okay, now let's say we decrease the voltage from 100 volt to 98 volt. And then with the same M prime, with the same parameters, everything else the same, what happens? Now if you look at the current, becomes VA into M prime minus VB, right? Here I use the final value theorem. You don't have to, because I haven't spoken about that. I will speak about that today later. But if you substitute here for M prime equal 925, for VB 40, for VA 100, 98, sorry, and then for R 10 milliohm, for RV 200 milliohm. So you see denominator becomes 210 rather than 10. So 21 times smaller. So in this case, the current will be 246 and the power will be 9.83. And originally, we wanted to have 10 kilowatt. Now we are having 9.83. This is acceptable, really. So again, if it's not acceptable, you can try to increase it a little bit, but keep in mind that you don't want to increase it too much. So for VB also, similarly, I showed here that now if VB changes 2%, the power goes down from 10 kilowatt to 9.95. This is again acceptable, really. And for R, now if R becomes 11 milliohm, and then again you calculate, the power becomes 9.95 again, so about 0.5%. So this virtual resistance is very common using virtual resistance, and I will talk about that more and more in the next few classes. It's very common in the control of power converters because you see it actually solves a fundamental problem. It's a very easy solution for a fundamental problem. And that's a feedback. You measure the current, you bring it back, and then generate a feedback loop. So basically what it says, and this is a thing that you may have heard from people here and there, we can never practically operate a power electronic converter without feedback. That's probably one of a few systems in practice that you cannot operate without feedback. There are other systems. Normally, you may be able to manage to operate without feedback, but power electronic converters, in any practical situation, you cannot operate it without feedback. And that's why control is very important for power electronics. If you are a power electronic person and you don't know control, you will have a hard time really managing. You need to know control. You may not be expert in control, but you need to know good level of control if you want to do research in power electronic converters. So now this simulation, I will run the MATLAB file as well. Basically, if you look at this simulation, we apply the command from 0 to 250. And this blue curve, is the original system without feedback, without virtual resistor. So it takes some time, like 200 milliseconds. You remember yesterday's settling time? It takes about 200 milliseconds to get there, but it gets there, no problem. But now what happens at this point, in order to check the sensitivity of the circuit, I apply a change. What is the change that I apply? I increase VA 2%, the same thing that was in the example. And then you see the current goes up significantly from 250 to 330, which is 34%. Now at this point, I bring back VA to the same number, 100, and I decrease VB 2%, I believe. Let me make sure, cases of without any. And then the yellow one, we'll see it, we look at the simulation. The yellow one is the case that now you have virtual resistance. How much? 20 times, the one that we did in the simulation. So first of all, we realize it becomes much faster. And that's something we did not talk about. The reason it becomes faster, because if you look at this transfer function, either here or here, if you look at this transfer function, the time constant of this transfer function is L divided by R plus RV. So once you increase RV, the time constant also goes down. Something that we did not start with, but we also get that advantage. So the response becomes faster. And basically, this is the reason that I told you need to watch out. Because when the response becomes too fast, and some of you may know, in control systems, if you increase the speed of a control system too much, other problems start showing up. And those problems are sensitivity to noise, sensitivity to unmodeled dynamics, sensitivity to nonlinearities, and sensitivity to delays that we have in the control systems. So you don't want to increase the speed too much. And then you see here, there is a little change, not much, and then again a little change here. So this second response is perfectly acceptable. Okay, let me see if I can quickly run the simulation. First time normally takes a couple of minutes, but then next times will be faster. Let's go. I thought my MATLAB is the slowest one, but this is even slower than mine. Yes, did you have a question?
We are talking about many control techniques,
Uh-huh.
like virtual impedance also when it comes to their connect converter and virtual impedance, everything.
Right.
Whether it is being applied in real applications, industrial applications, because I'm associated with one industry, they hardly go for that. They're strict
They
on
may not call it virtual resistance. That's only terminology. You will see later today that even a PI controller that you use, it is a virtual resistance. It has a virtual resistance in it. So they use PI, PID, those type of controllers. That P term in PID is virtual resistance. Does the job of virtual resistance. So you use PID, PI, right, all the time. That's it. PR, PI, PID. The proportional term basically is nothing other than the virtual resistance.
and is there any way to find out what is the upper limit of the virtual impedance?
Yes, like I said, the problems, the major one is, in my experience, the sensitivity to the delays. Because in power electronic converters, we have delays, digital control, PWM. So if you keep increasing the response to make it faster and faster, now the time constant of your response becomes smaller than the delays that you have in system. Then your system cannot work. So this response, time constant of your response should be sufficiently larger than total amount of delay that you have in the system. A few times at least larger.
Open the,
No, I think it's opening.
no sir,
It's opening.
you can click on this one.
Because I know it's opening. It takes some time. Because it doesn't show the prompt, it means it's working on it.
Meanwhile, if you want to ask any question, you can ask.
Yeah. Or I can continue with the teaching and then we come back and look at the simulation whenever it's on. Okay. Now, a couple of other general things. Now that we talked about virtual resistance, there is something else that is called input feedback linearization. It is very common in converters. What is that input feedback linearization? That input feedback linearization is basically the principles is shown. The principle is shown here. It says if my converter model is this, so it multiplies the modulation index into VA and then subtracts from VB. And I had a problem with sensitivity to VA and VB. I solved it to a certain extent, but let's say if it multiplies into VA, now can I divide by VA in the controller? If I can divide it in the controller, then this multiplication and this division cancel each other, so I completely remove the impact of VA. And now once you put a division here, this division and this multiplication cancel each other, so this we don't have this anymore. This block is completely gone. So now you have minus VB, okay, add VB here. This is very common. These are genius ways of dealing with some problems that people have developed over years. And then now you completely remove the sensitivity to VA and VB. Okay, you may say, why didn't we use this one? This is even better. Can anybody has answer to this? What is the problem with this approach? Or what is the cost for this approach? You need to measure VA and measure VB. To measure VA and VB, you need 2 voltage sensors. Okay. So if you can solve the problem, let's say you bring the sensitivity really close to 0, then why you add 2 more sensors? Okay. But if you want to add, you can add, no problem. Okay, not yet. So the next converter I'm going to talk after buck converter is boost converter, and you will see after I explain boost converter, I combine buck and boost together, and then we will come to voltage source converter, which is basically what we use for as inverter and rectifier. Now boost converter, the diagram is shown here. You see the switch and the diode, immediately you realize the power can go from side A to side B. It cannot go from side B to side A. So the power flow is from A to B. Now, how does this work? If you turn on this switch, this becomes short circuit. The voltage here becomes 0, and then you have voltage VA. So if VA is positive, then a current will flow here. So that's the first condition, VA being positive. The current will flow here. And that current will ramp up linearly, will keep going up. Like yesterday we said, if you don't stop it at some point, it's going to damage the switch. So at some point, what we do, we turn off the switch. Once you turn off the switch, what happens? The current will find a path through the diode. So this diode turns on automatically, and the voltage across the diode becomes 0, and this voltage across the switch becomes VB. Now assume, and that's the, again, fundamental aspect, that VB is larger than VA. If VB is larger than VA, now this current will ramp down. So the condition is VA is positive, VB larger than VA, for this circuit to be stable. So that's the reason it's called boost converter. Okay, now you can follow the same things that we did yesterday for the buck converter in terms of writing the switching function, like writing the voltage equation, deriving the switching model, deriving the average model, control model. I'm going to just quickly go through because you learned yesterday, and then you can always come back and read from here. So if this is the carrier waveform, and this is the modulation, when the modulation is larger than the carrier waveform, the switch is on, S is 1, and otherwise the switch is 0. And when the switch is on, the voltage across the switch is 0. And the switch is on, and when the switch is off, the voltage is equal to VB. And the voltage across the inductor, VL, is VA here, and VA minus VB here. So VA is positive, the current ramps up. VA minus VB is negative, the current ramps down. This current goes through the switch, this current goes through the diode. Okay? Very simple. And then analysis, you can write the equations like yesterday. So the voltage across the diode will be VB into 1 minus S2, which is S2N. Because when S2 is 0, S2 is 1, the voltage is 0. When S2 is 0, the voltage is VB. So that's the expression we have. And this is the voltage equation. So these two equations together give you the full model, the full mathematical model of the boost converter. Steady state analysis. For a steady state analysis, basically what you do, you put these derivatives equal to 0. If you put this derivative equal to 0, and then R is very small, so again you can even consider this to be 0. So VA is equal to and then for V you substitute from here VB into S2N. S2N is 1 minus D. And then I put capital D because it's in a steady state operation. This is not very important, but sometimes it's useful to have that information. So for the boost converter, the VB is equal to 1 over 1 minus D into VA. That clearly shows or confirms that the output voltage VB is larger than the input voltage VA. Switching model, yeah, the same as what we had yesterday. When the switch is on, the current flows here and then goes to the output through the switch. This is through the switch. And then when the switch is off, it goes through the diode. So if you have a simulation software that can simulate these components, that this resistor, inductor, voltage source, current source, you can simulate this one. And the response of this circuit will be the same, the response of this model will be the same as the response of your boost converter. For the average model, we follow the same procedure. We use DC and high frequency. Remember, DC and AC. And then you break down the equation to the DC part and AC part. This one, forget about it. We are not going to use it. That's the really high frequency dynamics, which for the purpose of control and operation, it's not important. For the purpose of EMI and switching operations, switching losses, those type of research, if you are working, you should consider that equation. Right? But for the purpose of control and operation, power transfer, those type of things, that equation is not needed. So, and M is equal to D, you really come across this model. So 1 minus M into VB, that will be the voltage across the transistor or the switch. And then VA minus VB is the voltage across inductor divided by the inductor impedance, that gives you the current. So this is the current control model for the boost converter. It has some similarity to the buck converter, because these converters are similar but not exactly the same. Input voltage control and output voltage control. So for input voltage control, this is, like I said, this is the circuit that we often use to increase the voltage or to control the voltage across a PV panel, and at the same time to increase the output voltage. So you put a capacitor here. Here you may have your PV panel, right? And then this voltage that you generate now at the output will be the voltage at the DC link, for instance, of your inverter. We'll talk about that later. Is larger than this voltage. So equations are very easy. 1 minus M into VB, that gives you V bar, this voltage across this transistor. V bar minus VA, that's the voltage across this one, or VA minus V bar, and then divided by the impedance of the inductor. That gives you the current flowing into this inductor, and this current minus this current becomes the current flowing into the capacitor. So this you can consider as an external current that comes from the PV, and then VA now is the parameter or variable that you want to control. And so if you look at this diagram, it has input modulation index that you forward to the PWM block, and the output is the voltage across the PV. So it's perfect for controlling the voltage across the PV panel. It's linear, fortunately. So boost converter, if you want to control the voltage across PV, it's a linear model. You can easily do that, no problem. For the boost converter, however, the output voltage control becomes nonlinear, and similar to what we had for the input voltage control for the buck converter. If you really look at these two converters, buck and boost, they are dual of each other. So the input voltage control of the buck becomes equivalent to the output voltage control of the boost, and vice versa. So it becomes again a nonlinear model here. Okay, all right, so now let's go to our MATLAB. I'm done with boost, and I'm going to combine buck and boost and derive voltage source converter. But hopefully we can run our simulation. Okay. So these simulations, okay. We can move them a little bit to the left. So I tried to add a couple of annotations to the circuit so you know what is happening. This is a buck converter here. This is a buck converter with virtual resistance feedback. This is a buck converter with virtual resistance feedback and VA and VB compensation. Exactly. So you put two sensors for VA and VB. So you have three circuits, and then each one has a PWM. So for PWM, you have the carrier waveform at the switching frequency of 4 kilohertz. And because this in Simulink, this carrier waveform is symmetrical between -1 and 1. So we push it up by adding 1 here. So now it becomes between 0 and 2, and you multiply into 0.5, becomes 0.5. Okay, so this is carrier waveform, and then this is the modulation. How much is the modulation? 0.425. So jump from 0 to 0.425. Okay. Here is the one that you have a feedback. So you measure the current. In this one also I measured the current, but I didn't use it. In this one I measure the current, and I bring it back here into this feedback loop, multiply into K. Remember K, 0.002. Subtract it. This is M prime. How much is M prime? 925, right? And then you generate the switch. So make sure you call it a different name for this switch. And the switch and diode are basically the standard blocks from Simulink. I think I chose ideal switches, no problem. Diode also, the ideal diode. And here I used a voltage source, controllable voltage source, so you can apply a jump. So here at VA, I apply 100 volt to 98 volt at the time of 0.5 second. And on this side also, I use controllable. So at 0.25, I decrease from 40 to 39.2, and then again at 0.5, I push it back to the same number. So I apply VB first and then VA second. Okay, and then here, if you see in the control, we have VA. So in simulation, you don't see it, but in practice, you have to put a sensor. for VA. So this is division block here. And then this addition with VB, no problem. And this is the virtual resistance. Now, once you cancel VA and VB, your virtual resistance, because remember RV was K into VA. Now you remove VA, VA becomes 1, so to speak. So it becomes exactly 0.2. Okay. Now, underneath here, these things, don't confuse them. These are, I told, control models. Control model. Always, the models that we derived, control models, you can use it beside your simulation, and you don't have to. If you don't like it, you don't have to. But in order to check that your simulation is running correct, one way is to check the response of your actual simulation with the response of your model, mathematical model. If they are close to each other, or you realize that everything is correct. So just to be on the safe side, I put the model. What is the model? 1 over Ls plus R. That's how to do it. And then M into VA multiplied minus VB passed through 1 over Ls plus R. This is mathematical model, mathematical control model. So I can look at the output of this also and check. So on this oscilloscope, I have all the waveforms, current I1, I bar, that's the current of the model. So current of the actual system for the first converter, current of the model, current of the second circuit, current of its model, current of the third circuit, current of its model. So all 6, so we can compare. And then here is to save the data and to plot if you want to show. So the oscilloscope should show all of them. Again, the first time normally takes a few seconds. This shows that something is running. You see, you can stop it or pause it, so let's wait. Okay, it ran, I guess. There you go. So this yellow one is the response of the system without virtual. I think I should have a legend on that. Let me see. Okay, the legend is here. I forgot to put the proper names to it, but you can do that. So this yellow one is the response of the actual converter without virtual resistance. That trace within it, without oscillation, without switching noise, is the response of the model. Because what did we do in model? We removed all the AC. So it's only DC. If you really zoom on that, this is the response of the actual circuit, current going up, down, right? And if you look at the ripples, there should be about 15 volts, 15 amperes that we calculated yesterday. And this is the response of the model, which pretty much goes at the average of that one. Okay. And this is the response of the system with the virtual resistance. You see, it takes about here is 5 milliseconds, so 5 milliseconds is there, almost, 5–10 milliseconds. If the delays that you have in your system, coming back to your question, is comparable with this, it's not going to work. But the delay, if it's less than, like let's say 1 millisecond, the delays that you have, or a fraction of a millisecond, it's going to work, no problem. All right, and this one, the pink one, is when you also use feedback linearization, input feedback linearization. So it's, if you look at the response, it's not sensitive to anything. Only maybe a little bit to the resistor, but with resistor we didn't check here. But it's not sensitive to VA, it's not sensitive to VB, it just exactly runs at 250 amperes, no problem.
Even virtual resistance is needed in input linearization. If it is not there,
If you don't put it, your circuit will be sensitive to resistance. Because feedback linearization fixes VA and VB, but not R. So it's good to put it there. All right. So with the simulations, there is a code here. And if you look at this code, and I run this code, it runs the same simulation and generates the figure that you have in the file. It's running now. After the run is complete, it plots the figure. Generates this figure for you. If you want to put it in a paper or thesis or something. All right, so let's also go quickly, a few minutes, if Chandra Shikaran has no problem with that, a few more minutes. Or should we stop here or continue? Can it stop? Because I don't want to change the schedule if there are online people. Try to come back in 10 minutes if you can, and if it's possible for you, because I'm a little bit behind my schedule. So.